everybody. Welcome to this very first research demonstration session that we've got here at AIUK. There's going to be 4 demonstrations for you in this session, and in between each one there's going to be a Q&A. So make sure you do submit your questions to Slido. I've got it here open to be monitoring, and I'll make sure to ask as many of the questions we can fit in the couple of minutes we have between each session. I'm sure the researchers would love to hear what you have to ask. If there's going to be lots of questions, of course, we'll pick the top rated. So if there's any that you really like, make sure you rate them, and I'll prioritize those ones to fit them all in. Without further ado, let's go into the very first presentation from Newcastle University. We have Cameron Kirk, Rana Zia-Raymond, and Sylvia Deldin, and they're going to be showcasing how can analysing the way we walk identify medical problems. I'm really excited to see this one. Let you all take it away.
Thank you very much, Gemma, and welcome everyone. Thank you for being in this session. I'm Dr. Sylvia Deldin, and I'm here today with Cameron Kirk and Rana Raymond. They are 2 PhD students that are working in the Brain and Movement research team at Newcastle University. This demo has been also co-designed in collaboration with Professor Paul Watson, who is the Alan Turing lead at Newcastle University. So show me the way that you walk, and I'll tell you about your health. We propose this provocative title as some of you might not know that how we walk, so our gait, is considered the 6th vital sign. Yes, like blood pressure, body temperature, gait can serve as a tool for evaluating our health. This is because gait, so the way that we walk, not only reflects mobility function, but more importantly, brain function. So if brain function deteriorates because of disease, this affects the way that we move and walk. Typically, gait is measured with the use of expensive systems, for example, 3-dimensional motion capture systems that are limited to being used in specialized clinics or lab facilities, giving only a snapshot for clinicians of the real capacity that people have to move, in their real world condition. So wearable technology, think about your smartwatch, Fitbit or smartphone, can really help us translating this into the real world by enabling remote and continuous monitoring of mobility across days and weeks. So using wearable technology, our team, and in collaboration with Professor Paul Watson, has developed protocols together with diagnostic algorithms and AI models for clinical application, specifically for identifying risk, for example, disease like Parkinson disease, and track their progression across the time. In this demo, we will first present a short video on how we can use wearable technology for gait analysis, and then Rana will show a practical example of how the application of AI to walking data can really help the diagnosis of Parkinson's disease.
Hello everyone, my name is Rana, a Marie Curie Fellow working at Newcastle University. As we just saw in the video demonstration, the gait performance is considered as a marker of global health, predicting mortality, morbidity, falls, and neurodegenerative disorders. However, in this talk, we will discuss about the management of Parkinson's disease using machine learning and gait analysis. Parkinson's disease is considered as the second most common neurodegenerative disorder after Alzheimer's, by affecting 10 million people worldwide. As the world population is getting older, the prevalence of the Parkinson's disease is also increasing. Sadly, there is no cure for Parkinson's disease. Only its accurate early diagnosis can help in its better management. The current diagnosis is based on subjective clinical scales. The average diagnostic accuracy is only 26% on first clinical visit, ranging from 53% if the disease is present for less than 5 years to 88% if the disease is present for more than 5 years. So there is a need of practical, affordable tools, objective tools, which can be used for the management of Parkinson's disease. Parkinson's disease has both motor and non-motor symptoms. The motor symptoms assessed with gait analysis are typical in PD, appearing early and evolving over time. Usually the gait analysis is performed in a high-tech gait laboratory. However, with the help of wearable sensor, we can assess the gait outside of the laboratory, which can be more sensitive to the classification of the Parkinson's disease. But the real-world gait data bring its own challenges, as we have different activities of daily living, and we need to deal with big data. As you can imagine, the sensor is attached at the lower back of the subject for 7 days, and we are recording the body acceleration continuously at 100 Hz frequency. So the big question came to our mind, can we use AI to make sense of this big data? In order to provide an explainable AI solution, we did the feature engineering of gait, where we extracted meaningful clinically relevant gait characteristics and divided them into 5 domains, representing pace, rhythm, variability, asymmetry, and postural control while walking. Additionally, from the accelerometer signal, as shown in the graph in the middle, we utilize the full potential of the accelerometry data by extracting the novel characteristic representing different domains such as movement intensity, movement smoothness, movement regularity, and symmetry. Further, these characteristics were used for the classification modeling. Based on the feature engineering of gait, we trained and tested almost every classifier for binary classification of the Parkinson's disease from age-matched controls, where the input to the model was the gait characteristics and the output was the disease label, such as the Parkinson's disease patient or healthy older adult. Based on our experimentation, the models such as spot vector machine and tree-based models such as random forest and XGBoost were optimal for the classification of Parkinson's disease with gait data. If we compare the classification or diagnosis performance across Parkinson's disease assessment from clinic and from laboratory gait and from real-world gait, our real-world gait approach, where we assessed the gait continuously for 7 days, gave better classification performance as compared to others. So the vision of this research is to be used as a pre-screening tool for the management of Parkinson's disease remotely, where the participant can assess their performance automatically over time. And in case of red flag, they can visit the clinic and show the model results to the clinicians, and clinicians can have accurate, informed clinical decision based on that information. Therefore, to summarize, gait analysis paired with AI can transform the management of Parkinson's disease. So this is just a first step in the right direction. Thank you, everyone.
Thank you very much for that presentation, Rana, and for the video and from the introduction from you as well, Sylvia. We've got one question come through so far on the Slido for you guys from Christina Varitimidou. I'm so sorry if I have got your surname mispronounced there, Christina. Are all data retained to improve accuracy? Is this application solely ML or DL? Who's going to answer that out of the three of you?
Okay, I will answer that. So we can utilize both approaches, ML and DL, but as we know, the clinicians need an explainable solution. So we can feed that model directly to the neural network, but in the end, we will not be able to know what gait characteristics are really impaired, which can actually help them to propose an intervention at later stage. I agree, the DL approaches can give us better results, but clinicians want an interpretable solution.
Thank you very much, Rama. And I'm going to add one question as well on top of that I was curious about. What's the sort of next step for the project? Where are you going now?
So the next steps are actually to test these models on a early stage Parkinson's disease cohort dataset, where the where they call it a predromal cohort data set, in which the people are assessed longitudinally over time. And if we can assess them maybe 5 years or maybe 1 year or 2 years before having actually diagnosed the Parkinson's disease, that will be great. So that is our next step, to actually test these kind of models into clinical practice and testing them further.
Great, and we've got a couple more through. I'm going to do quick fire questions of these two. Hopefully we can fit in both of them. First one's from Colin Patterson. How sensitive is the system to sensor placement? Can a patient apply them themselves?
Sylvia, can you answer?
Absolutely, we had quite an extensive, if you want, testing with this. We have used the sensor in a variety of clinical trials, and we have really developed robust methods and models that, if you want, are really looking and taking into consideration the slightly misalignment of the sensor. So we have a process to realign the sensor, and we do allow the participant to attach and retouch the sensor as they wish and as they need to. So yes, it can have an impact, but we have developed methods to really take that into account.
Brilliant. Another question from Barbara Melville Johansson. Would this work with people who have existing conditions like back pain?
Absolutely. So the concept here is really to provide a tool for remote monitoring and, you know, in the long term for remote clinical management. So we have started looking at, you know, older adults and looking at neurodegenerative disease like Parkinson's disease, but also like a lot of work in dementia. But obviously this has the opportunity to really be applied clinically to a variety of cohorts and pathologies as well.
Okay, I'm going to take one final question. There's loads of them flying in here now, but we've got such a limited time. Final one here from Ian Hamilton. Can the gait data be augmented by laboratory data to increase accuracy further?
Yeah, like if we see the pattern or distribution from the lab and real world, they are totally different. The people in lab are walking faster as compared to the people in real world. So merging them together, for example, from the same subjects, their distribution will be different. They will impact the model definitely. Like we can treat them as a separate data points for training, but based on our experimentation, the real world is more sensitive to classify these kind of populations.
Amazing. I'm afraid, sorry for everyone who we didn't get to your Slido questions. I'm sure the researchers from Newcastle Uni would be happy to hear from you separately if we've not had time to take your questions here today. But we're going to move on to our next presentation. Thank you so much to Cameron, to Rana and to Sylvia for presenting us your work. But next up we have Professor John Moriarty from Queen Mary University of London, and he's going to be showing Wrangle, I hope I've pronounced that correctly, a competition platform for forecast-based control problems. John, take it away.
Hi everyone, my name's John Moriarty. I'm Professor of Mathematics at Queen Mary University of London, and I lead the Wrangle team at the Turing. So what are competition platforms? Well, they're web-based and they host data science competitions. They provide a problem description, any supporting code, some data for training, and they also take care of evaluation and ranking at the end of the competition. Competitions are usually time limited and offer some level of monetary reward. And the really powerful thing about them is that they're open to any person or team in the world. To check out examples, you could have a look at Kaggle or AI Crowd or CodeLab, and there are some great others as well. And actually, we're going to see an animation now that's just going to show you what it looks like to interact with our platform Wrangle. So if we could start that, please. So Wrangle's part of my AI for control problems project at the Turing. It's using something called OpenAI Gym for the challenge code, and the platform front end is based on the open source Eval AI, which has lots of useful features, but it enables in particular industry, to upload their challenges of interest, and then enables participants to register for the challenge, to work on their entries, and then to be evaluated and ranked at the end. And across all of these different great platforms, there have been some fantastic challenges run to date. So, for example, Manchester City sponsored a challenge which was around developing an AI to play a football video game. The Microsoft Kinect platform, Kinect games console sponsored a challenge around gesture recognition. And CERN also sponsored a challenge around detecting certain decay patterns of the Higgs boson. So I think those three examples illustrate the power and the scope and the breadth of this approach. So what do we mean by forecast-based control problems? Well, Wrangle is inspired by the use of forecasts in long-term problems of planning or short-term problems of controlling electrical power systems. So it's these sorts of infrastructure challenges that we're focusing on. The roots of our approach are proven. So we worked with Electricity Northwest, and we're helping them save £5 million in costs, and also to reduce the embedded emissions in their electricity distribution network. The novelty of the Wrangle platform is that it enables reinforcement learning to be applied to problems of this sort. And indeed, we have a focus on really democratizing the use of RL for these sorts of problems. So the project is open source. We try to make it as easy as possible for industry to create a challenge, and of course as easy as possible for participants to compete. In case you haven't met RL before, so it has its roots in two theories. So firstly, how animals learn by trial and error, and also the mathematical theory of how to control systems in an optimal way. And in RL, learning comes by playing repeatedly in an environment and learning from the consequences of actions taken. So there's no explicit teaching needed in RL. And that's what makes it easy to apply and general also as a solution technique. And the agent, the learner, has to take a series of short-term actions in order to reach its longer-term goal. So, for example, RL has been successfully used to help train robots to walk, to help teach autonomous cars to drive, and famously to beat the world champion at board games like Go. So we ran our first Wrangle challenge a couple of months ago, and that was around using forecasts to schedule power generation and thereby to limit as far as possible the use of fossil fuels. And we had 10 great teams from around the world participating, from academia, from industry, and from the third sector. We didn't insist on the use of RL, but actually RL did win. It did outperform other approaches tried. And actually the winning team was a group of power systems engineers who themselves actually had limited prior experience of using RL. I can share that we have another challenge planned for early next year, which will be around using economic forecasts to find the most affordable pathways to net zero carbon emissions for the UK offshore industry. And that challenge will be a collaboration sponsored by the OGTC. So I'd just like to end with a word of thanks to the Lloyd's Register Foundation, who have funded the work, and the fantastic members of the Wrangle team. I'm happy to take any questions.
Thank you very much, John. That was absolutely fascinating. We've got a couple of questions already come through from Slido, but if anyone else wants to get their questions in, do it quickly and we'll try and ask them all. So the first one is from Mark Basham. What sort of prizes, i.e. value, are needed to get a good uptake of participants? So
our first challenge didn't have cash prizes, but it was 2 times oversubscribed. So uptake is fine. I suspect that if there had been cash prizes, the competition itself during the week might have been a little more fierce. So that's the difference I think that the prizes make. But I think there's a massive demand for people to get their hands on the use of RL in real problems.
So you think it's about the realness then that's the kind of what gets the uptake?
And also the opportunity to get into RL, yeah.
Okay. Awesome. Let's go to the next question from Mark Daniel. Wrangle or industry challenges, etc. They look interesting, but how do you protect the company data used in the challenges? Does it have to be hosted at the ATI?
Yeah, so typically we'd be using synthetic data. The idea of, I think in general of competition platforms is to sort of find the mapping from the sort of problem to the sort of solution technique. So, you know, ultimately what we want at the end is an understanding of how to approach the problem more generally that will work on multiple different sets of assumptions, multiple different sets of data.
Awesome. Next question is from Simon Ellershaw. Do you provide compute to aid democratization?
Yes, if we have it, then we're very happy to share it. So the competition is hosted in Azure, and yes, the sponsors, you know, provide a certain level of cloud computing credits. Yeah.
Great. From Andre Fernandez, thanks for the presentation. That's nice. Did previously existing open source platforms like OpenML have any particular limitations that favored a new platform?
As I said, there's lots of nice platforms out there. We took a look at all of them, and we tried to use what we saw as the leading approaches. But I think that, you know, the thing that's distinctive about Wrangle is the focus on the kinds of problems. So we're really trying to partner with industry and get RL democratized and used in these infrastructure problems.
And we'll just squeeze in a wee one because it's kind of related to that from Anonymous. What's the USP of this platform compared to, say, Kaggle?
Yes, I think I just refer to my previous answer. It's really the work that we're doing in going out and speaking to industry in the UK and working with bodies like the OGTC to understand and to demonstrate how to use RL through challenges and to get that out to as many companies as possible.
Amazing. Thank you so much, John. And thank you everyone for asking questions. We hopefully snuck in as many as we could just then. But let's now move on to the next presentation. We're hearing from Dr. Charles Day and Adam Wooten. They're from Keele University, and they're going to tell us all about novel machine learning for improved non-destructive testing and monitoring in the natural and built environment. Welcome, Charles and Adam, over to you.
Hello, Gemma, and hello, everybody. We've got our video all prepared, I hope, so if we can run the video, we'd be happy to deal with any questions that come after we've had a chance to look at that. Hello there, I'm Charles Day, and for this demonstration session, I'm joined by my colleague, Dr. Adam Wooten, who will help me later to field any questions you might have arising from this presentation today. The particular part of the built infrastructure we've been addressing ourselves to in this study involves steel reinforced concrete. You can see an example of that in the picture at the side here. It involves, when the structures are made with steel reinforced concrete, embedding steel meshes inside the concrete structure before it sets. Once it's set, the concrete can be percolated by water, so when it's used on elevated sections of roads, motorways, road and rail bridges, that sort of thing, water can ingress, and hidden from view, there can be rust and corrosion that takes place against the important parts of the steel reinforcement. Sometimes some of this rusting and corrosion is visible on the surface of the concrete, many times not. And it's when there are no visible signs of this corrosion that we've tried to address our machine learning and AI techniques in this problem domain. This causes all sorts of problems, some problems more or dramatic than others. You can see some examples on the right-hand part of this slide. More mundanely, for the particular focus of this research work, we've been trying to see if using our tools and techniques from Keele University, if we can improve estimates of the maintenance cycles and the duration of the maintenance cycles on elevated sections of roads and motorways of the sort that's been carried out for an extended period recently, for instance, in the West Midlands and the M5 Junction 1 to Junction 2 Albury Viaduct repairs. And we'll return to some of the issues that arise from that a little bit later in this presentation. The tools and techniques from Keele University, which we've been deploying to try to address this, involve a special, non-invasive electromagnetic anomaly detection probe, which relies on properties surrounding magnetic flux leakage. This EMAD probe can be swept across the surface. As you can see Adam pushing the Mark II EMAD probe in the video clip now. It sweeps across the surface of a steel reinforced survey site, and the data that's acquired by the EMAD probe carries a data tablet in the handlebar region of the Mark II probe. Back at the lab, hitherto, we've been able to analyze the data streams from the EMAD probe so that we can see anomalies that have been identified as a result of analyzing those magnetic flux leakage signals. What we've been trying to do with our AI and machine learning is trying to automate the interpretation of that data to see if we can get accurate and, most importantly, fast estimates of where the problems are while the survey is taking place. The techniques we've been using from AI and machine learning to do this involve recurrent neural networks. Specifically, we've been using echo state networks, or ESNs, as well as, more recently, from the deep learning stable, some of the long short-term memory neural networks. Anyway, echo state networks and LSTMs are well suited for processing time series style data, such as the multidimensional time series data that we get from our EMAD probe. We use these data sets with regions of survey sites with known defects as training data for our recurrent neural networks, and the outputs from our neural networks can readily be translated into heat map forms. The idea is, once the neural networks, which are always problematic to train, of course, the ESN's less problematic, but still takes some time. But once trained, the pre-trained networks can be used with real-time flows of data from the EMAD probe to produce these heat maps and hopefully be displaying the heat map on the data tablet of the EMAD probe in close to real time as the EMAD surveys the survey site. In some of our latest doctoral research, we've been fusing the EMAD magnetic flux leakage data signals with information about the depth of the steel reinforcement beneath the surface of the concrete. It's easily obtained by attaching a cover meter to the EMAD probe, and these fusion recurrent neural networks can give improved accuracy, but once they're trained, of course, still fast heat map outputs, which could be displayed on our data tablet. Returning briefly back to the real-world nature of the problem, that extended period of work which was programmed on the M5 in the West Midlands a few years ago, once the concrete and surface coverings were broken open, an extra 4,500 hitherto undetected defects were detected. We'd like to think that if we could have surveyed the site before any of the concrete surface structure was broken open, we could have identified a fair proportion, at least, of these 4,500 defects before the work was actually carried out. So that would have meant we could have made a better estimate of the extent to which the motorway might have to be coned off and the duration of the works that might need to take place. And you can see an example here in this completely artificial simulation of a traffic flow on a simulated piece of motorway. There's a little coned off region of just the near side carriageway here in this simulation, and this extensive rolling roadblock which is propagating backwards along the traffic flow on this simulation. It did start off near the coned off section, but when I made this recording, it had already flowed a significant way backwards along the motorway carriageway, and we've got all of this standing traffic as a result of this rolling roadblock. The issue here is not just the time, having better estimates of the time and money to carry out the repairs, but getting improved quality on those estimates so that we can minimize the duration of this standing traffic so we can reduce CO2 and NOx emissions and dangerous particulates. One of our undergraduates is looking at how we can augment this traffic flow simulation to give a better handle on the excess CO2, excess NOx and excess particulates that might be being emitted by the cars, vans and lorries in this simulation as a result of being slow moving traffic. Even when we eventually manage to get the entire fleet on our roads electrified, the issues don't disappear, because whether we got electrified or hydrogen powered cars, we still have extended journey times and delays to traffic flows through important parts of our infrastructure. We're seeking to give better maintenance cycles, improve maintenance cycles to reduce these delays and hiccups to journey times. And there'll be benefits that arise even post-electrification for that. Finally, these are some of the people who aren't with us for the demonstration today who've made important contributions to this work. So thanks to all of those folks as well. Thanks for your attention today.
Thank you very much for that, Charles and Adam. That was really fascinating. I don't think we have any questions through just yet on the slide that was specific to your presentation. It looks like we've got a question for the previous presentation that's just come through. So while we're waiting, I'm going to ask you the same question as I asked the others, because I'm always fascinated. What is the next step for this research? Are you looking for collaborations? Are you looking for new types of places to implement your results, your data? Tell us a little bit about that.
Well, I'll jump in and try and deal with that first, Gemma, if that's okay. Don't want to talk over Adam if he wants to say something as well. Well, the EMAD probe has been used commercially for a number of years. It's actually, although Professor Haycock owns the IP for the EMAD probe, it's actually already been used for doing commercial surveys under license with the company. One of the big innovations we're very keen to do now, though, that we can analyze the data quickly and efficiently using the machine learning, is the potential to actually have the EMAD probe, rather than just being pushed along on that sort of baby buggy Mark II instrument that you saw Adam pushing in one of the video clips. There's the possibility for even avoiding coning off the motorway if the EMAD probe could be arranged, say, on the chassis of a moving vehicle close to the road surface. It might be a slow moving vehicle, but there might even be scope to conduct surveys of important, say, motorway infrastructure without even having to cone off the motorway. Now, we've never tried this in reality. We've worked all the time. All of our data analysis has been with the push-along version of the EMAD probe, but we think that's a highly attractive proposition. Over the last few weeks, we've been, our little group has been liaising with industry partners who have expressed an interest in using some of the EMAD, the proven EMAD facilities. But that idea about the possibility of having the probe suspended beneath a moving vehicle, that's not distant, but that's still science fiction at the moment. We'd love to collaborate with people possibly and see if we could try that out for real.
Brilliant. Okay, let's move on. We've had a question come through on Slido from Nick Mrozchak. Sorry, Nick, if I've got your surname incorrect there in the pronunciation. What is the time dependence of the data that warrants the use of RNNs as opposed to CNNs?
Well, the time series, that what we found is that with recurrent neural networks, where of course the idea of processing a time series with a recurrent classifier, say, is that as well as looking at the instantaneous signal that you get at a particular time instant, we found that there are characteristic patterns in the signal as it evolves through time, as the EMAD probe sweeps across the surface of the survey area. And it's by using, if you like, the short-term memory that you get from recurrent neural network techniques, that you can get improved classification accuracy, rather than a sort of instantaneous analysis as you might get with at least the traditional use of, say, a CNN convolutional neural network. I think the question you talk.
I'd add to that as well that in that characteristic signature, one of the things that we look at is a rate of change in one of the magnetic components that we consider. So there's implicitly a time domain in that rate of change. So which is part of why the recurrent networks are so good at processing it.
Amazing. Thank you both Charles and Adam for coming in and sharing with us your projects. We don't have any other questions come through right now, but for anyone who does have any extra thoughts that we haven't had time to get to today, I'm sure both the researchers would be happy to take questions over email or getting directly in touch. Of course, if any of you are using all the different rooms and hop in, I'm sure there's a way of chatting to each other, perhaps even during the conference. Okay, let's move on to our next presentation. Thank you so much to Charles and Adam. We're going to take our final demonstration from one of our silver sponsors, which is Intel. And from Intel, we're joined by Alexey Gruzdev, who's going to talk to us about federated learning. Alexey, over to you. And that's you live now, Alexey.
Okay. Hello, everybody. So my name is Alexey Gruzdev. I'm leading a Russian team which is working on the OpenFL library, which is an open source library for federated learning. And today I would like to give you a basic sense of what is like federated learning is and how to use our library. So if we start from the very beginning, so every deep learning researcher knows that without data we can't do anything. And if we like typically analyze the case how we work with data, so typically we have the data annotated and being already placed in kind of a central server, and then we can train the model out of this. But if we would analyze how data is born, so we would know that data is born in distributed fashion. And sometimes we have limitations such as like privacy, like the size of the data and like valuability of the data that actually doesn't allow us to transfer the data and have this like a vanilla scenario with deep learning. And federated learning typically handles this problem. So if we can't transfer the data, so what we can do? Basically, what we can do, we could transfer compute to the data, yeah, and we could come up with another scenario, which is like a distributed world scenario. And if we analyze this right picture, so let's say that we have 3 hospitals here, and we can't transfer hospital data because that's there is a restriction, so we cannot move this data. What we can do, we could actually place a server inside like each hospital to train its own model, yeah. But as we know, like the more data, the better model. If we if we're doing like everything correctly, yeah. If we train the model with the right capacity, choose right hyperparameters, and etc. So how can we train like a central model out of this scenario? So we could have an aggregation server, and for each particular hospital, which has like its own data, we could train model number 1, model A, model B, model C, and then send them to the aggregation server to be aggregated in some fashion. And then updated model could be sent back to these hospitals for next training. And that what is like federated learning in a nutshell. So let's move to the OpenFL library, right? So at Intel we are developing this open federated learning library, which is open sourced, and basically it's open sourced under Apache version 2.0 license, so it can be used in commercial project. It supports TensorFlow, it supports PyTorch, and we have like examples of how it can be used with MNIST data, brain tumor segmentation, histology, polyp segmentation, tiny ImageNet, and adversarial training. In terms of the interface, we basically have 2 scenarios. So one is like a Python API, and another one is a command line interface, which could be available for the fix command. So Python API is dedicated to the experimentation and basically is constructed for the data scientists. Yeah, and this like a fixed CLI is constructed for the production settings. So in order to run on multiple machines, you have to use this fixed CLI interface. Yeah. So right now I'm stopping here the presentation. I'm going to present the Jupyter notebook with our example of how we could use this from Python API. So how do we install our library? We are basically calling like pip install OpenFL, and our library is available through the PyPy. So basically here I have an environment and already pre-installed OpenFL. So I don't need to run this command, but typically you could use it just like from the like vanilla PyPy installation. So we are installing Torch if it's not installed, because this is a PyTorch example. Yeah, and then in order to integrate like OpenFL inside like PyTorch example, what we are calling like what we need to add to our code, we basically need to create and initialize default workspace. And here we have a predefined default workspace for our unit and quasar data. So let's initialize. On the workspace, what we have a predefined data structure that is related to specific certificates, which is like for the data, and for the like giant configs for like basically for federated learning hyperparameters and settings and collaborator settings as well. Here it's a normal piece of the code that could be like bringing. I bring this code basically from the like vanilla unit example, and here what we should add only like we should add these two lines for the importing like our entities, which is a federated model and federated dataset. Yeah. Once we have these imports, we could download the data. This is quasar data set, which is basically for the like a polyp segmentation task. Yeah. Then we have a normal code, which is just like a PyTorch code, so no modification from our side related to defining definition of quasar data set. Yeah. And here we have an entity which is called like quasi-federated data set, which is a wrapper under this federated data set, our entity. And the main goal to have this entity is to have this split method in order to set up like a arbitrary number of collaborators, let's say 2, 3, to work in this kind of scenario. Next, we have a definition of UNet model. And I'm skipping this part because we don't have any modifications. This is just like a copy paste from the PyTorch example. Yeah. And here what we are creating a file data instance, which is a quasi-federated data set. Yeah. So once we created this data, we could set up the model. And for the model we are building, so we have this unit optimizer, soft dice flows, and the data loader, which we already defined. Yeah. Once this is done, so we could set up the federation. So federation, we are just calling the methods with a number of collaborators too. That means that we have two hospitals that would train the model. Yeah. And once this is done, we could basically print our federated learning plan with a bunch of like settings. And then we could run the experiment itself. So here we are just like calling and to train 2 rounds. Yeah. So it starts training, and once the training would end, I could show the kind of the final result of the model. We could save this model in native PyTorch model format, and then reuse it in any of the like normal code without any federated learning stuff. Yeah, and we could even like plot the results and see how well the model trained or not. And I believe that here for me to stop and start answering questions because the model is training, and after it ends, it would take a few minutes, and after it trains, I would show the results, like what we get at the end. And the only thing that I also want to add is that we have our Intel booth, and my colleagues Olga and Patrick would give like a much detailed overview of what we are doing. So if you're interested in federated learning stuff, so please join the Intel booth for any of the federated learning questions. And thank you for your attention, and I would be pleased to answer any questions right now.
Thank you very much, Alexei. That was really fascinating. Oh, we've just had one question through now. I was going to say we'd have a little pause to wait for them to come through, but let's go to this first one from Giulio Giacconi. In a nutshell, what is the difference between this library and the federated learning capabilities on TensorFlow?
As far as I know, for federated learning in TensorFlow, we have a TFF, yeah, which is a TensorFlow federated. And we are focusing on the kind of a multi-node scenario. And here I'm showing a single node Python API example, but in general, so we are focusing on the multi-node scenario that could be deployed in multiple hospitals. And as far as I know, so for TensorFlow federated, they have like very nice API, and in terms of like research vehicle, it could be like a great choice. Yeah, but if you go like in some real world scenario, so most probably you will miss some capabilities.
Amazing. Let's go on to the next question from Mark Daniel. Have you developed metrics that allow you to compare the performance of a centralized learned model versus a federated learned model?
Oh yeah, that's a great question. So basically the training actually ended, and so here we could see like the result of the, here is the target and here like prediction of our model. And I'm sorry for bad pictures, but that's medical stuff, you know. As for the specific metrics, I would say that this is a question of research, and right now, like it's an open question. But generally speaking, we are comparing some models like a centralized training versus like a federated scenario, right? And I would not say that in all cases we are better compared to centralized, but in many of them, like we could achieve like a greater accuracy.
Awesome. Next question is from Alex. What anonymization may be necessary when only few data / encryption methods exist for the local models when federated learning is employed for privacy reasons?
I would say that here we are trying to solve the problem of data, so we are not moving data to this central node, yeah. But as for the model, yeah, so here another techniques should be applied, because as for the model, so here we are exchanging like model snapshots, and if anybody could actually hack and get the model snapshot, that's basically possible, but that's not a federated learning kind of a problem. Yeah, that's another question.
Amazing. Thank you very much, Alexei. And actually, I'm gonna sneak in another question just quickly for Charles and Adam, if it's possible to bring you both back up onto the stage at all. Sorry for the technicians at the back. I'm being disruptive by doing that. But we had a couple of questions come in after you finished, and I didn't want to miss out on asking them. One question that actually got repeated by two people was basically asking, can this technique be applied to other kinds of detectors, e.g. for archaeology, or applied to other structures? That's questions from Julio and Alistair.
Well, I'll try fielding that one to start with. Adam can chip in later. The presentation we just presented there, we've only applied the work to the EMAD probe data. It's multidimensional. As Adam was saying, there are time series components to the EMAD data, which means it's quite challenging. It's also noisy data because of the depth dimension. We combine some depth meter, some multi-sensor data fusion to give even better performance. And the nice thing about that is that works well in the presence of noise as well. Now, it depends on whether in those other applications, whether similar sorts of recurrent neural networks techniques would be necessary if the data streams were, as with our EMAD probe, are multidimensional and were characteristically time series in nature, really, Gemma, I think. Without more knowledge about the particular data streams that the questions we were talking about, I'd really be shooting in the dark a bit there. I don't know if Adam wants to add anything to that.
No, I don't think there's anything extra I can add to that. I think that covers it. You know, there's a wide range of applications, but without knowing what the data is, it's difficult to say.
There's clearly a lot of interest from people, you know, asking about other structures, other kinds of detectors, and also Parma has asked about whether it could be used to analyze interior built environments. So clearly, lots of interest from everyone from all of the presentations today. Thank you so much to all the researchers for your presentations and for everybody watching for all your questions. This has been absolutely brilliant to see some of this AI in action as the session has been titled, and I hope that everybody watching has enjoyed seeing all this research being presented.